at. So let's look at this topic of coatings and surface engineering. And this is something that manufacturing people are more involved with as compared to the previous topic. Again, coatings and surface engineering is a very, very broad area, as we all will agree. So I'm going to just narrow our focus to just a few topics here. I'm going to look at just these different processes. Thermal spray coating processes, PVD, CVD, plating, anodizing, surface hardening, and a little bit about paints and powders. And if I run out of time, then I may just stop wherever I am. So let us first look at why we modify a surface. So why do we make changes to a surface? Why do we coat something? And here are the well-known reasons for that. Protect the surface against corrosion and oxidation. For example, galvanized steel. You apply a zinc coating on steel to reduce corrosion. Create thermal barriers or diffusion barriers. So sometimes we modify or coat a surface to create thermal barriers to reduce heat loss, or diffusion barriers to reduce contamination and chemical reactions. Another reason is to improve wear resistance or durability. So when we apply carbide coatings on cutting tools, multi-layer coatings on a cutting tool, then our main objective is to increase the durability of the cutting tool material so it can last for a longer time. And it also has high wear resistance. And finally, we want to have some kind of an aesthetic appeal. The surface should be pleasing, and that can be achieved, for example, in color anodizing. You're able to create parts that have color as surface. So one or more of these reasons could be why we want to modify or coat a surface. So as just one example of how challenging it could be to design, and I'm going to look at this example. Electrodes used. Molybdenum is a refractory metal, high temperature metal, and it is used as electrodes in many types of furnaces, including in glass melting furnaces. And these electrodes are used to about 6 become an insulator. It cannot serve as an electrode. So the solution was to apply a coating of molybdenum disilicide to prevent oxidation of moly. But then it caused a new problem. Expansion between the coating and the substrate caused cracks. Mismatch between the expansion caused cracks. So the new solution was to match the expansion by adding silicon carbide to the coating material. So the expansion of the moly silicide coating there was a new solution that you sputter coat another film to create a diffusion barrier. So the idea here is to tell that developing new coatings or surface treatments is a very complex, iterative process. To come up with a solution that causes a new problem, come up with another solution. So this kind of a self-corrective approach is quite often used to develop new coatings. Before you can apply a coating or modify a surface, you may have to consider all these different factors, operating conditions of your part, the compatibility of the coating and addition to the substrate, what kind of substrate we are using, what surface preparation is needed, what is the application method of coating, and the speed of application, safety and environmental factors. A lot of processes of coating involve toxic or harmful effluents or carcinogens like formaldehyde or cadmium. So one has to be really careful about VOC or volatile organic compounds and other toxic substances. Part design considerations, properties of coatings, and the cost factor involved. So all of these have to be considered when you select coatings or surface treatments. One thing we have to always remember is that the part to be coated or modified should have its surface cleaned before surface modification. And another thing to remember is that high quality coatings will not excuse poor surface preparation. And likewise, high quality surface preparation will not excuse poor quality coatings. So the quality of the coating as well as the quality of the surface preparation of the work piece are equally important. So to get started, just look at these basic processes of how we clean surfaces. And we all are, I'm sure, familiar with these basic processes. Abrasive cleaning, a process like sand blasting that can be done in a glove box compartment, or you can have um, in an enclosed room, large parts can be surface cleaned by using mixture of steel shot with pressurized air or sand with pressurized air to remove any surface contaminants. Quite often people use dry ice instead of sand. They use dry ice, which is basically solidified carbon dioxide. So the advantage here is that there is no dust formation because dry ice will impact, clean the surface and sublimate to form gas, CO2 gas. And CO2 is non-toxic. So sometimes people use dry ice as an abrasive material. Tumbling is another surface preparation method where we use an abrasive medium and parts to be cleaned inside a rotating drum or tumbler. But obviously you don't want to fill the tumbler completely. There should be enough room for this kind of a relative motion to take place between the work and the abrasive. And the relative amount of abrasive and the workpiece have to be controlled. If you have very little abrasive, then cleaning will not be fast. In fact, there could be damage because of impact of one part on another. If you have too much abrasive, very few parts, then again, cleaning process will slow down. Production will slow down because you are cleaning only a few parts in every cycle. So the ratio of abrasive to number of parts to be cleaned is important. And you can select abrasive media depending on the shape and size of the surfaces to be cleaned. So like if you want to clean this kind of a wedge here, you want to have a different shape of the abrasive particles. But tumbling is another way to clean the surface. Vibratory cleaning. You put the part to be cleaned and the abrasive in a vibrating drum like this, and the whole mass is under vibration or agitation. Typically, vibratory cleaning is a little faster than tumbling because the whole mass is under agitation, not just the surface layer where cleaning takes place as in tumbling, but vibratory cleaning provides faster cleaning. So all those three methods work for removing mechanical impurities, slag, oxide scale, sand inclusions. Those processes don't work on chemical impurities. So if you have oil, residue, fluxes, grease, any chemical contaminants, then you cannot use these processes, obviously. You have to use chemical methods. And we know that we use alkaline solutions or acidic solutions to clean the surface. You use ultrasonic cleaning processes, or you use what's called vapor degreasing process. In vapor degreasing, we put a solvent, the cleaning solvent, which is mostly a halogen-based halide solution, in a tank here. And this solvent has a very low boiling point. So when you heat that solvent, vapors begin to rise, and you put your work to be cleaned on the top here. So the vapors will condense on the part, and then you wash the contaminants with the same solvent. With a jet, you can wash off the impurities. So with time, all the impurities continue to fall in the tank, but the vapors continue to be clean because this is a low boiling point solvent. So the cleaning action can continue for a very long time, even though the solvent gets contaminated. So this is another way that people clean parts. So once the part has been cleaned, then you are ready to apply coatings or modify the surface. So I'm going to look at some surface modification or coating processes. Let's look at thermal spray coating. In thermal spray, we actually melt and spray the coating material on a surface. So you can use some kind of a plasma gun or even a welding torch to melt the feed material and create droplets that will impact the surface and build up the deposit. It could be a fully automated system. A robotic system can be used, like in this case here. You can have multiple nozzles simultaneously coating the surface here. And this whole thing can be done under either atmosphere or under high vacuum to reduce contamination. So deposition of molten droplets on a surface, that is what thermal spray is. Coatings grow by rapid solidification. And feed material could be either powders, wire, or rod, just like in a welding gun. Thermal spray coatings are about a little over 100 years old. Sometimes around 1917, first demonstration was done with zinc coatings. In the 1950s, refractory coatings came up for aerospace engines. In the 70s, vacuum plasma spraying came up, and then other innovations came. So the main reason for applying thermal spray coatings are these here: to form hard wear resistant coatings, to apply thermal barrier coatings, and to deposit corrosion resistant coatings. These are some simulation results from the literature on thermal barrier coatings on an aluminum piston. So by applying the thermal barrier coatings, you are able to get higher temperatures in the piston, and that increases the efficiency here. Now, it is possible to use a thin coating of a ceramic as a thermal barrier in these kind of applications, right? In a furnace or in an oven, we need a very thick fire brick lining for insulation, right? But in an IC engine, we don't need a thick wall. We just need a thin coating of ceramic. And the reason for that is that in an engine, we don't have a continuous heating process. It's a combustion cycle. So the coating does not respond to thermal changes very rapidly, and you have one thin coating which is sufficient. In a furnace, you have a continuous heat, so you need to have a thicker lining or fire brick lining. So what are some application areas of thermal spray coatings? I have listed some here from the literature. In petroleum and gas search drilling installations, you apply chromium oxide and superalloy coatings for wear and corrosion resistance. In automobile alternators, you have aluminum that is thermal sprayed with aluminum oxide for salt corrosion resistance. In textile machinery and food processing equipment, the textile fibers, they continuously come in contact with rotating steel drums. So there is wear of steel drum from textile fibers. So now people replaced steel drums by lighter aluminum drums, and they applied chromium oxide thermal spray coatings. So now you have lighter drums with the same hardness and wear resistance as steel drums. Another application area is adiabatic diesel engines. Thermal barrier coatings, they allow combustion gases to do work instead of heat being lost in the cooling system. So ceramic coatings are used, zirconia and yttria based coatings are used, but you need a bond coat. Just like in the case of polymer coating, when you apply a paint on a surface, you may have to have some kind of a pre-coat or bond coat. The same thing is needed for high temperature systems. So you apply a bond coat of a metal like cobalt chrome, and on top of that, you deposit the ceramic coating. Aero engines and marine gas turbine engines, they utilize thermal spray coatings. Turbine blades are thermal spray coated with these kind of coatings. A metal, high temperature metal, nickel or cobalt, together with chromium, aluminum, and one of these refractory metals. And these are used for oxidation, corrosion resistance at high temperatures. Landing gear components, their hard chrome has been replaced by nickel aluminide. Hard chrome is pretty hard, but nickel aluminide thermal spray coatings are even harder. Rocket thrust chamber liners, they have plasma coatings of ceramic materials, oxides, over some kind of a bond coat. Tungsten carbide cobalt, wear resistant coatings for compressors. We know that tungsten carbide cobalt is also used as cermet in cutting tools, right? So the same material is used in compressors of engines. So these are some of the other application areas of thermal spray. It's a very, very wide range of applications. So here you're looking at the efficiency of gas turbine engines or temperature operating temperatures of gas turbine engines and their historical development with years. So in the 1950s and 60s, mostly wrought alloys were used. Later, we had conventionally cast alloys. After that, we had directly certified alloys, single crystal alloys. So these innovations, the temperature capability of the engine kept on going up. And these single crystal alloys are now coated, thermal spray coated by thermal barrier coatings. So again, there is a step up jump in higher temperature capabilities. So this is where technology is right now. So thermal barrier coatings have given a lot of advantage in terms of improved engine power and efficiency. These are some data on thermal spray market in the United States. The projection is in terms of several $billion of revenue for thermal spray coatings. So in a gas turbine engine, this is just a cutout of the gas turbine engine. This is where the air comes in. This is the compressor. So the air pressure builds up. This is the combustion zone where you have a fuel and air mixture ignited. And then you have the turbine that are propelled and the combustion exhaust gases are exited from here. So the turbine blades are coated with ceramic materials for corrosion resistance, high temperature corrosion resistance, because the operating pressures and temperatures are very high. You have 40 atmosphere pressure and temperatures could reach 1400 or 1500 Celsius. So no alloy can survive those temperatures without ceramic coatings. So turbine blades are coated with different ceramic oxides. And this is what the cross section of the coating looks. This is the substrate. It could be a nickel superalloy, single crystal. Then you have a bond coat, which could be a metallic bond coat, nickel or cobalt based. And when you deposit the bond coat, there could be some interdiffusion. So you have some intermediate layer also, a diffusion zone. Over the bond coat, you thermal spray the thermal barrier coatings. And this is a thin oxide film between the thermal barrier coating and the bond coat. So this is what the cutout of the turbine blade looks under high magnification. This is the external coating, which will protect the part from corrosion, high temperature corrosion. This is the bond coat region for good adhesion. And this is the actual turbine blade. This is how thermal fatigue properties tested for thermal barrier coatings on turbine blades. This is one version of a General Electric's thermal fatigue test. So this is the workpiece or substrate, and the yellow thing is the coating, the thermal spray coatings. So this is the actual workpiece with the coating on it. You blow cold air on the back side and flame on the coating side, as you see here. Then after a few seconds, you move it up to the cold zone here. You blow cold air on the hot coating, which is shown over here. Then you again bring this down and expose to the flame. Again, move it up to cold air both sides. So you repeat this cycle hundreds and thousands of times, and then you look for cracking or chipping or debonding of the coating. Very practical test to check the quality of the coating, thermal spray coatings. And based on that, you can find the thermal barrier coating lifetime as a function of temperature for different types of coatings. Some other applications of thermal spray coatings are in electronics industry, carbon electrodes. They are thermally sprayed with metallic coatings. Heater rolls in laser printers, faxes, and copiers. They have thermal spray coatings of copper zinc ferrite or cermet. They help reduce the warm-up time. Boilers in power generation plants. because boiler tubing in coal power plants is exposed to steam at high pressures and burning coal, and coal can cause corrosion and erosion of the steel tube. So to minimize that diffusion of carbon, thermal spray coatings of nickel chrome are deposited. Similarly, you have applications in iron and steel industry, in blast furnaces, in rolling mills, in extrusion dies. So thermal spray is a very, very important area of coatings for mostly for high temperature applications. How do we apply thermal spray coatings? These are some standard methods. Atmospheric plasma spray. So just like a welding gun, where you mix the right proportion of oxygen and a fuel gas like acetylene. And that mixture is ignited and you feed the coating material in the flame. It melts and it exits at a high velocity because you have pressurized air. So the molten droplets will strike the surface and form the coating. So a simple welding gun can be used, or you can have arc spray process where you have a powerful arc that will melt the feed material to form the coating. Atmospheric plasma spray. Instead of using a combustion fuel, you can use an ionized gas like argon gas, create a plasma, and plasma gas can go to very high temperatures, 10,000 to 14,000 degrees. And practically any material will melt even in a short residence time, microsecond, something can melt. And if you want to deposit silicon carbide coatings on a surface using an oxyacetylene flame, you cannot do that because the flame temperature may be about 4,000 degrees. And if you put silicon carbide powders in the flame at 4,000 for a microsecond, they won't melt. So you really need plasma gun or some very high temperature system. So plasma spray is used. And if you have a vacuum system to reduce contamination, then you have a vacuum plasma spray process. HVOF, high velocity oxide fuel spraying. Here you have a very high pressure that the flame is under very high pressure. So the speed is very, very high here. Or detonation gun process or degun process, where the thermal spray process is intermittent. So many 18 or 20 cycles per second. So because of that intermittent nature, the workpiece does not get heated up too much during the deposition process. So there are different ways to melt and form the coatings. And here you're looking at the temperature of the process and the velocity of the droplet for different processes. You can see that the velocity of the droplets could be very, very high, 800 to 1200 meters per second, or 400 to 1000 meters per second. That is the droplet velocity at which the droplets come out of the nozzle. And depending on the distance workpiece, the workpiece also will have very high impact. So very often the surface of the workpiece might be pitted because of yielding. When you have a bullet striking the surface at high speed, you have yielding, but also very good bonding. So temperatures are pretty very high. Here you have the data for different thermal spray processes for porosity and bond strength. So as we can see that, there is a lot of scatter for different processes, but by and large, if you have less porosity, then the bond strength is higher, which is something we expect. So these are just the abbreviations of some of the symbols here. What kind of a structure does the deposit have? Well, mostly it is a sort of a brick wall structure because you're depositing layer by layer. The structure of the coating in cross section is like this layered or brick wall structure. And there could also be some defect in the deposit, voids, oxide inclusions, any unmelted particles of the coatings, all of those things can happen. But typically, the thickness of the deposit, each splat is just a few micrometers thick. And the solidification time could be just a few microseconds. What is the temperature in front of the gun nozzle? So we have a nozzle out of which the droplets are coming out, and then spray. How does the temperature of the droplet in the spray vary with the distance from the torch exit? So this is the central line temperature in front of the nozzle, gun nozzle, as a function of distance from the nozzle in millimeters. And these are the data for plasma gun. You can see that right at the nozzle, the temperatures could be about 12 or 13,000 degrees Kelvin. And in about 4 centimeter distance ahead of the nozzle, the temperatures had dropped to about maybe 5,000 degrees. So there is a very steep temperature gradient in front of the nozzle. And these kind of considerations help you determine the working distance between the nozzle and the actual workpiece. Similarly, the second graph shows you the radial temperature distribution, which means you're looking at on the x-axis, you have the distance from the torch exit. So this is the distance along the center line. And on the y-axis, you have the radial distance. From the center line, you're going perpendicular to the center line axis. And you're looking at how temperature changes in the radial direction. And these are isotherms, constant temperature lines. And you can see that maybe over, if you go from this point to this one here, this is the maximum temperature range change. So maybe over 4 millimeters, the temperature might have dropped from 10,000 degrees to about 1,000 degrees. In other words, when you have a spray cone, a cone of spray of molten droplets, the outer droplets might solidify rapidly during the spray process. Similarly, the velocity changes, especially if you're doing plasma spray in air, then the viscous drag of the air will cause the velocity to drop very rapidly in front of the gun nozzle. So those are the kind of considerations that we have to look at when you design the thermal spray process. And what is the effect of some of these parameters? If you have a high linear velocity, which means the gun is moving very fast in the workpiece, then you're depositing very small thickness in each pass, because the gun will return to the initial position faster. So you have a slower deposit formation, but the good thing is that there is less oxidation and less cooling. If the gun comes back to the initial position faster, then the liquid has not yet solidified, and you have the next layer and the next layer depositing. So you will have less temperature gradients in that deposit, less corrosion from atmosphere. So high linear velocities are good from that point of view, that you have a cleaner, better quality coatings, but the process is slow because you are moving the gun faster for a given flow rate, mass flow rate. For low linear velocity, you can deposit thicker coatings per pass, but then you have more time for the layer to cool down before the next layer deposited. So there could be temperature gradients and thermal stresses, those kind of issues. And this is just a thermal scenario for how things can happen. Maybe we can skip this one. That's more about the thermal process. We can skip all this theoretical analysis here. So let's move on to another coating process. Let's look at the physical vapor deposition and chemical vapor deposition process, PVD and CVD, very commonly used methods. So one example of a PVD process is vacuum metallizing, which is simply heating and evaporating the coating material under high vacuum and letting the coating vapors deposit on a substrate. So that is a process called vacuum metallizing. And this can be done on like plastic or paper. So when you have plastic rolls or paper rolls with thin metallic like aluminum coating or gold coating, this is the process they use to deposit coatings. So heat the metal or the alloy, let the vapors form, let the vapors rise and condense on the workpiece. And this must be done under vacuum because you don't want air molecules to scatter the vapors of the atoms. Now, because the deposit thickness is extremely small, when the vapors condense, they don't generate too much heat. So there is no danger of paper or plastic getting burned by the heat released from deposition process. So thin metallic coatings, zinc, aluminum, cadmium, those are deposited using this process. Parts can be rotated, they can be fastened to racks, or you can match certain areas of the workpiece and selectively expose some areas for deposition. You can have multiple vapor sources for coatings of different types to be formed. And the workpiece is initially at room temperature, but it may heat up due to vapor condensation. Now that is possible only if you're depositing a very thick coating. For normal thin PVD coatings, there is hardly any temperature change in the workpiece. And vaporization is difficult for metals with low vapor pressure. You need a much better vacuum if you want to deposit metals of low vapor pressure. So from that point of view, a metal like aluminum, which has a very high vapor pressure, is very easy to deposit. You don't need very high vacuum to deposit aluminum by vacuum metallizing process. The second PVD process I'm looking at is sputtering. There are different types of sputtering processes, magnetron sputtering and others. Sputtering is also used when you want to prepare your samples for scanning electron microscopy examination. Sometimes non-conducting surfaces need a metallic coating, and we use a sputtering unit to deposit the coatings. And the good thing about sputtering is that you don't have to heat anything. The process is done at room temperature. So the idea here is to have a tungsten filament that is electrically heated and it begins to emit electrons. Now electrons are accelerated inside this chamber toward this positively charged anode. And as the electrons build up speed, they collide with the residual gas in the chamber. Usually this is argon gas. So when electrons collide with argon molecules, the molecules get ionized, they create plasma or ions of argon. Now ions of argon are positively charged, so they're attracted toward this negatively charged target. And this is the coating material. So argon ions will go strike the target and eject coating atoms. And those coating atoms will deposit on the workpiece. So all of this is done at room temperature. There is no need to heat anything. The only problem here is that during sputtering, because the atoms of target are going in all directions, sometimes the vacuum wall, the chamber wall also gets sputter coated with time. So you lose some sputtered material, but still you are able to get good coatings on your substrate. So this is done mostly at room temperature. The bonding is very good because coating atoms strike at high velocities the workpiece. And this is different from vacuum metallizing because in vacuum metallizing, you have only vapors or atoms of vapor rising. They don't have very high speed. So they can be destroyed by air molecules. You need better vacuum in here as compared to in the sputtering process. And because the coating is not vaporized, very refractory coatings can be deposited. Coatings of very high melting point, they can be deposited by this process. It's just a picture of copper coating on carbon fiber. The carbon fiber itself may be about 7 or 8 micrometer across, but look at the thickness of the copper coating, less than a micrometer across. So you're able to build up almost atomic layer coatings. Applications of PVD are in decorative coatings on molded plastics, on metal coatings on paper, optical coatings on optical systems like mirrors, headlamps, and lenses, corrosion-resistant coatings, especially cadmium and aluminum on steel to prevent hydrogen embrittlement, and then electrical and electronic applications. Resistors and capacitors, they have multi-layer systems. So the metallic coatings are deposited using the PVD process, as in this case that we saw earlier last time. Chemical vapor deposition. CVD is basically an actual chemical reaction. Unlike the PVD, in PVD there is no chemical reaction, there is just change of phase. In CVD, we have gases that react with one another over a hard surface. And one of the products of reactions is the actual coating that builds up the part. So different types of cutting tools, drill bits, they are all coated using CVD with very hard coatings. So these are the actual CVD chambers. vacuum chambers with heater coils. So the interesting thing here is that coating forms by reaction between gases, not by reaction between the work and the gases. That's the difference. The gases react with one another, and one of the products of reactions is the actual coating. Uh, so vapors have to be selected, or gases have to be selected carefully based on thermodynamic considerations, so that one of the products of reaction is the coating that you want to form. And sometimes the decomposition products are toxic. They have to be flushed out. So you have to have a disposal system to neutralize any toxic gases. Borides, carbides, oxide, nitrides, and many other kinds of films can be formed. And the gases that are used for reactions are mostly halogen-based compounds of these metals. So just as an example, if you want to deposit these hard coatings of titanium diboride, you can have different chemical reactions that you can use. Now, in this first reaction, you have these three compounds. They are all gases. But when they react at high temperature, they form one solid compound, which is the coating. So I can use this reaction to form the coating, or I can use the second reactions. Again, these two compounds on the left-hand side are gases. But when they react, one of the reaction products is the solid compound. So you can have multiple reactions to form coatings. How do you select which reaction to use? Well, you use basic thermodynamics, free energy calculations for reaction changes and everything. Again, we'll not get into those details because this is not a materials or metallurgy focus. Similarly, you have to look at the transport phenomena, the diffusion process, the convection process, and the actual reaction at the interface. What are some applications of chemical vapor deposition? What kind of parts are made? An example is titanium nitride coatings. So this is a substrate, and on top of this, this is a TIN, titanium nitride coating. Triple coated carbide cutting tools. So on a cutting tool like this, you have three layers, really hard layers. You have the outer layer of titanium nitride. The second layer is aluminum oxide, and below that, you have this titanium carbonitride layer. And then here you have the workpiece. So these kind of multi-layer coatings are formed by CVD, or carbon coatings on a surface, creating rhenium foam. That is done by CVD, growing carbon nanotubes, single and multiple wall nanotubes by CVD, or ceramic coatings on powders. So in this case, you have a heater around this tube, and you put the powders to be coated in this chamber. You turn on the heat and blow the gases, the reacting gases from the bottom up. So this becomes like a fluidized bed, and the gases react with one another and deposit the coatings on the powders. Or CVD can be used to make ceramic composites, things like carbon-carbon composites. So CVI is just another name. It's called chemical vapor infiltration, which is basically CVD as an infiltration process. So what you do here is you have the carbon fiber bundle inside the vacuum chamber, and you introduce reactive gases in the chamber. The gases will flow through the fibers and also around it. But the gases, as they flow through this, they react with one another and they deposit carbon between the carbon fibers. So with time, you create a carbon-carbon composite that has carbon fibers inside and amorphous carbon powder that is deposited in the fiber. So that composite is used to make brake discs and several other components. So these are some applications of the CVD process. Let us switch to plating and anodizing processes. Another group of important processes for surface modification and coating. Plating and anodizing. Electroplating. We know electroplating is commonly used to deposit all kinds of metals. You can even deposit composite coatings, which means you can co-deposit diamond powders with a metal or very fine carbide nano powders with a metal by electroplating. But it has to be a conductive substrate on which you deposit the metal. The commonly plated metals are chrome, nickel, and many others. Practically any metal can be deposited because most metals are good conductors of electricity, so electroplating can be done. Ionic species are used instead of charged particles. Deposition of charged particles is electrophoresis, but electroplating uses ions to form the deposit. One problem with electroplating is that if you have deep holes or crevices, the deposition is not very good. The holes are not very uniformly filled in electroplating process because of current density being different in a cavity versus on an external surface. So there could be some issues because of the curvature. And in electroplating, you are depositing very, very thin films. So covering surface imperfection could be difficult. Unless you have a very thick deposit, the surface imperfections may not be completely hidden. So why do we electroplate? Well, parts have to be electroplated with wear and corrosion resistant coatings, or electroplating is done also to restore dimensions of parts that have been worn or machined outside the acceptable tolerances. Electroplating processes can be automated. There is no theoretical limit to the thickness of the deposit. Because you're depositing conductive metals on a surface, there is no electrical breakdown. And that's a little bit different from powder coatings. In powder coatings for polymers, we use electrical charge and paint particles. And paint particles are insulators. So once certain thickness of thermoplastic or thermoset powders is built up, there is electrical breakdown, and you cannot go beyond a certain thickness. But in the case of electroplating, that problem is not there because you are depositing conductive metals, so you can continue depositing very thick film. Of course, from a practical standpoint, you don't need very thick coatings, so a certain amount of thickness is enough. It's not a line of sight process, and any surfaces that don't need to be coated can be masked by a non-conductive tape. Electrolyte has to be stirred either with jet motion, air jet motion, or work motion. And the composition of the electrolyte has to be controlled. One of the main things is that you want hydrogen not to be sticking to the workpiece, because there could be hydrolysis of water when you pass electrical current, and that hydrolysis can generate hydrogen. And if hydrogen bubbles stick to the workpiece, they can diffuse. Hydrogen can diffuse and make the metal brittle. So you have to be able to remove hydrogen continuously from the electrolyte. We'll not get into the chemistry here, but some practical things about part design. If you're trying to electroplate a part like this with a curved surface here, then you want to open up the lip here. You don't want the electrolyte to be trapped in this corner, and that would serve as a corroded area down the road in surface. So we want to remove all electrolyte from getting trapped. Or if you're electroplating a tube or a hollow part, then you must have a little drain hole to drain the electrolyte out. Otherwise, the electrolyte inside can cause corrosion later on. Any sharp corners should be made curved, again, because there could be thermal stress buildup during the deposition process. Mostly we have either batch type coating, or more often it's a continuous strip plating process. So you have a steel sheet or steel cables that go through the plating tank continuously at high speed in the electrolyte, and they get film deposited. So this is the process that is used to form copper coatings on electrical cables or galvanized steel. Those kind of parts are electroplated using continuous plating process. The interesting thing is that the speed of the strip through the tank would be very high. Typically, the speed is almost 300 to 400 meters per minute, which may be about 5 or 6 meters per second. That is the speed at which the strip is moving through the plating tank. So very rapid production process. Some design considerations here. The shape of the anode and the positioning of the anode should match the surface that you want to plate. So if you have this kind of a surface, you may not get a uniform deposition on these ends here. If you have an L-shaped section, if you position the anode like this, the inside corner will not get much deposition. But if you change the orientation of the anode, deposition is thicker. So one thing I forgot to mention, and probably people know that is the workpiece that you want to plate should be the negative in the electrolyte. It should be the cathode, and the anode could be a dummy metal like a tin or something else, or the anode could be a consumable electrode, which means it will serve as the source of metal. So anyway, the positioning of the anode is important. In this example at the bottom, you have a triangular cross section to plate. If I use one anode, I will not get any deposition on the back side. So you may have to use 3 smaller anodes to get a uniform deposition. If you have a cylindrical part to plate, you cannot use a flat anode like this. The anode has to match the shape of the part to get uniform film. For a section like this, triangular cross section, you may have to put thieves or robbers or burners to steal away some of the deposits from the corners. These corners are high current density areas, so the deposition will be thicker here as compared to the flat area. If you want a uniform film throughout, you may want to steal away some of the deposits here, which means you put some conductive parts in the tank in these corners to remove some deposition from them. Or you can put non-conductive shields near these corners, plastic shields, to reduce the current density and reduce the amount of deposit. So all those things are done in practice to make parts. I have about maybe 15, 20 minutes or so roughly, or 15 minutes or something. Okay, all right. So here are some examples of metals that are most commonly plated. Gold is plated for decorative purpose, but it is also used in high technology applications because gold has a very good electrical conductivity. So it is used in printed circuit boards as interconnects here. Lead and tin alloys, they improve soldering, and they also provide corrosion resistance on PC boards. Copper and brass, they are electroplated. Copper is used in printing rolls and PC boards. Brass is used for decoration, but also used as plate on steel wires. Quite often, brass plated steel wires are used to reinforce rubber tires for high strength. And brass is able to bond with rubber better as compared to steel. So steel wire is brass plated for good adhesion with rubber. Chromium. Chromium used to be plated for good corrosion resistance and low friction. Bumpers of cars, wheels, and extrusion dies and those kind of things, they are coated or plated with chromium. And zinc is used for galvanizing, mainly for steel. Just like you have electroplating, we have electroless plating, which doesn't require any electricity to form metallic coatings. So you can deposit metal coatings on non-conductive substrate. In this picture over here, we have polyimide films before deposition. This is polyimide before deposition, and this is after gold deposition by electroless plating. Or polyester fabric, which is non-conductive before deposition and after deposition by gold. So even non-conductive surfaces can be plated with metals using this approach. One advantage of electroless plating is that you get uniform deposition on the inside corners also. So this is difficult to achieve in electroplating. In electroplating, a thin inside hole may not receive any deposition, but in electroless, you're able to get more uniform deposition here. So that's the advantage of electroless. And the disadvantage is that quite often electrolysis tank, the electrolyte and the electrolysis process needs more frequent, fabrication. You need to keep checking the composition to maintain the right composition. So there is good and bad stuff here, but please go ahead. Oh, yeah, okay, I'm not looking at that here, but the basic process is, again, it's a multi-step process. So in the first step, of course, you have to clean the part, solutions, and then you have an activator solution. I have used this process in my PhD work 40 years ago. I was depositing copper and nickel electrolysis coatings on silicon carbide powders. So we had to do that. So you have to clean powders, then transfer them into an activator solutions, and then a catalyst, which was palladium chloride based solution. It was a palladium compound. And then it was a solution in which you have the nickel or copper salts. So you leave the part in there, stir it at room temperature, no electricity, and after some time you will be able to get deposition. Take it out and dry. So yeah, it's a multi-step process. But again, that's a very standard process. I cannot recall the steps, but it's all very well known. I can provide you some information if you need that. Yeah. Yeah.
They have changed some chains.
Change, yes.
They have changed of the silver watch, silver.
Okay.
Is it possible to the electrolysis plating on different silver chain?
Yes, it is possible, but my understanding is that electrolysis plating does not give you very smooth or uniform deposition. So maybe if they are using for wristwatch, if they are using electrolysis, then I'm sure they are polishing or doing something afterwards to get a real good smooth finish. As deposited electrolysis films are not very uniform or smooth. So I'm not sure if this particular, are you saying that they use electrolysis plating on this chain here?
We have I'm looking to traditional family. My father also doing the
Okay.
Grandfather.
Okay, so it is actually useful.
One axle, another axle, two known, two together.
Yes, yes.
वो हाथ से बनाया करते थे.
Yes, yes, yes. Yes, yes.
Axle बनाया करते थे.
Yes, yes. Lot of.
Technological domain है, उसको कैसे elaborate किया?
Okay, okay. Yeah, there is a lot of practical skill that is spread all over. It has not come to the knowledge of people who make decisions or who research. That's unfortunate, but that's the way it is.
Yeah, tradition to technology. Traditional to technology.
Yes. Tradition to technology.
System है.
Yes.
Technical domain में कैसे access किया?
Yes, yes. That's an important consideration. I agree. That's where the focus should be actually of the government and authorities who work. They should be convinced to bring the technology that is already there and bring it to the knowledge of people. Yeah, that's a good point. All right, I just quickly finish things here. Anodizing is another coating process. What is anodizing? Anodizing is nothing but oxidizing the surface of your part with the help of electricity. So if you take a piece of aluminum at room temperature, on the surface it is not aluminum. You have a very thin native film of oxide. But that oxide film is not very helpful. It's so thin that it does not prevent further oxidation or it does not provide any wear resistance. So by anodizing, you just make that oxide film thicker with the help of electricity. That's what anodizing is. So electrochemically depositing hard inert oxides on any metal, that's anodizing. Dielectric films on electrolyte condensers, oxidation corrosion resistant films. Anodizing also improves addition of liquid paints on the surface. And anodized surface could be decorative because you can impregnate pores of the coating with dye, colored dye, and then seal the pores to have very nice colors on the surface. Anodized coatings are always very porous on a nanometer size. So those pores can be impregnated. And because oxides are electrical insulators, when you anodize the surface, you are actually creating electrically insulating surface. And oxides are very hard materials, so the wear and abrasion resistance also improves. And you can have batch type anodizing or continuous coil anodizing. Again, you have multiple steps in the anodizing process. Uh, Batch anodizing is done on extrusions, cookware, cosmetic cases, flashlight, and everything. Continuous anodizing is done on sheet and foil and light fixtures and reflectors. Say it again. Yeah, exactly. That's another. Yeah, cookware includes the pressure wear. Exactly. Anodizing is used for that, both for corrosion resistance in cooking and for oxidation resistance. Yes. So again, we'll not go into the chemistry, but this is a high magnification picture of what the anodized surface looks like. So this is almost nanometer size. So you're looking at very fine pores on the surface of the anodized part. And depending on the thickness of the anodized film, you have different application areas. If you have very thin anodized film, then the surface conditions should be very mild. And as the thickness of the film is higher, the surface conditions could be more severe. So I think maybe is my time pretty much up? 5 minutes? So maybe I won't go into the new topic. Maybe I'll stop. And then if there are questions or discussions, we can go over it. Is that okay? Yes. All right. Okay.